Okay, so the next speaker is Michel. He was working at Max4 before. He is working at ESRF now, as far as I know. In any case, he is a Python expert, a maintainer of PyTango, working now at the Beamline control team at ESRF. And he will talk about using reactive patterns and approaches for Tango.
Thank you. So, hello everyone. So this talk is about reactive programming and how it fits within control systems. So the slides are available online if you want to follow this presentation on your devices. So what is reactive programming? It's an asynchronous programming paradigm, and it's about data streams and the propagation of changes. So it's tightly related to concepts like pipelines, for instance. So this is very abstract, but if you've done a bit of Python, you might know about First things first. Let's talk about languages like Python and C. They're called imperative, and when you use the equal sign in those languages, what you're actually doing is an assignment. So you're computing the value of A plus B and you're assigning the value to C. So if A or B are updated in the future, then C will not be updated. But in reactive programming, however, what you're doing is you're writing definitions. So in this case, if you define C as A plus B and A changes or B changes, then C will change as well. So you don't have to maintain the integrity of the variables yourself. I mean, that's part of the reactive machinery. So how does that work in practice? If you've done a bit of Python, you might remember about Python properties. So you can, it's a very simple syntax. You decorate a method, and this magically becomes a property. So you define it with a simple relationship, C equals A plus B. And then if B changes and you ask for C again, then you will get the updated value for C. However, this is not asynchronous. So this is not really reactive. Whenever you're asking for C, the value will be computed again. So it's not very efficient. So it doesn't very fit into the paradigm, but still it still has this concept of descriptive interface. However, if you take languages like QML or the Kiwi language, those actually implement a reactive approach. So I don't know if you're familiar with those languages, but what you end up with is a tree representation of the widgets in your application as a YAML tree, like in this example. But what's on the right side of the code is usually, it's either JavaScript in the case of QML or Python in the case of Kiwi. And you use this to define simple relationships between the property of your different widgets. So in this case, this is a Kiwi application with two text inputs, one label, and the label is simply defined as the sum of the number in the two text inputs. That means when you run the application, if you ever update any of the two text inputs, the result on the label will be updated automatically by the Kiwi or the QML machinery. So you don't have to write anything more than that. That's enough to run the application. Another approach to reactive programming is more explicit. It's called a constructive approach. And this is what the ReactiveX library does. So there's a Python implementation called RxPy. And this is how you define what they call observables, which are in fact just simply data streams. So in this case, A will count from 0 to infinity every second. B is simply A delayed by half a second. And then we can create C as the combination of A and B, and the values will be combined by a function that we can pass, and in this case, it's the sum. So it's yet another implementation of C equals A plus B. And you can see in this so-called marble diagram that the data streams are going to behave as we expect. Why is it useful, and when is it useful? Well, if your system is already using events, then it's probably a good fit, because the event-based communication channels are already very close to observable or data streams, so you can easily build a reactive system on top of them. What's good about it is since you don't have to maintain the integrity of the variables yourself, then you have less state to manage, your program is less functional, and you have less bugs in the end. Also, if you provide an abstract, a descriptive interface for declaring those relationships, then it hides the implementation logic so that developers can focus on business logic instead. So that also means less bugs. But now, how does this apply to control systems? Well, this is my very biased representation of control system based on my experience. So you have hardware control, data acquisition, monitoring, and data processing. And the way I see it is the upper part is synchronous. Usually for hardware control and the data acquisition, you really want to have precise control over the workflow and what's going on. So everything is usually very synchronous. But on the other side, for data processing and monitoring, that part can definitely be asynchronous. And if the upper part is pushing events, then you can build the whole monitoring system or data processing system around data streams and using reactive programming techniques. And I'm not so familiar with data processing, so now what I'm going to talk about is mostly monitoring, because that's what I've done. And I think there's a golden rule in monitoring. It's monitoring shouldn't affect the world. So it doesn't matter whether the monitoring system is running or not. This shouldn't affect your experiments. However, there are a few exceptions to that, and this rule doesn't always apply. For instance, if your experiment includes a cat in a box that is both alive and dead at the same time, then monitoring your experiment will cause your cat to collapse, which is usually not a good thing. But apart from this case, then I think it's a rule we should stick to. And it has a few implications. That means the monitoring system should never trigger a hardware request. And in order to protect the hardware from the monitoring system, you probably need a system agnostic service that is closely managing the hardware and protecting it from external agents. And that means this system will not care about the number of interested agents. It could be 0, 1, or 1,000. The hardware should work the same. And this is how you build a reliable system. At least for the I'm talking about monitoring here. So how would you get the hardware values then? Well, this service could write to a cache, which is perfectly fine, and then the monitoring agents will simply read from the cache. But it introduces latency in your system, so a way better approach is to use PubSub, so publish, subscribe, and event channels, basically. Does that mean that we should give up on RPC? Probably not. Remote procedure calls, they're fine for running explicit commands. And that's because commands are usually the result of a user decision. So your system will be affected because of a user decision. But the monitoring system is not a user. So I don't think it makes sense for the monitoring system to use RPC in this case. So in practice, what can be done reactively? Well, all kind of simple computations, really. Could be applying conversions, so converting units. Could be integrating values over time, so compute the charge out of a current, for instance. Also, it's definitely useful to combine values together to create, for instance, logical conditions that you can use in your alarm system. And so if I'm talking about this, it's because that's been implemented at Max 4 as part of its monitoring system through so-called facade devices. Those facade devices are actually Tango devices that will subscribe to Tango events and publish Tango events. There are more than 3,000 such devices running at Max 4, and they're mostly sensors and actuators in practice. So they will represent equipments at a higher level. So if we get back to our C equals A plus B example, you can see that it's very similar to the Python property syntax that I presented earlier. In this case, addition will be a facet device. It will get A and B from 2 Tango event channels. It will compute, whenever something happens, it will compute a new value for C, and it will broadcast it to the network through event channels as well. So you can build multi-layers on top of that. The library is available on GitHub. It's documented, it's unit tested, and it is actually released on PyPI, so feel free to give it a try. If you ever used any of those concepts in your control systems, then I'm very curious about it, so please come and talk to me. I thank you for your attention.
We have time for some questions.
And some kind of concurrent system, concurrent processing in some process to yield other process. And in that time, this conclusion it's same because some kind of justification, the timing or something. So that active, reactive method is okay. I'm not understand what kind of a system. Okay.
I'm not sure I understand the question.
It's a concurrent system. It's
yes.
Two process communicate and sometimes yield over each other, and that time different and value in A or B or something in different timing. So it's still okay for this kind of system.
I think so. Yeah. In any case, those concepts they fit very well with a concurrent system, and so I mean it's really tied to asynchronous programming and stuff like this. So yeah, it usually works, but it really depends on your implementation of the reactive machinery, because those concepts are very high level. So you have to use a reactive machinery that can deal with concurrent access, for instance. So it can be tricky to implement, and it really depends on the tool you're going to use.
Okay. Thank you very much for your presentation. It was very professional, and I liked it.
Thank you.
Okay. So my question is about, you were using Python in your examples, but have you considered strongly typed languages, like Haskell or something? Because I see you were utilizing very functional style for things, and I think that having a strict type system would even enhance these approaches. Yeah, probably. Those problematics are very orthogonal, in my opinion. So I'm sure you can implement those concepts in many languages. But in the case of functional languages, then it's definitely it's something quite popular, actually, called functional reactive programming. There's a whole field of research about it, I think. And I'm not so familiar with it, so I don't want to say anything wrong about it, but there are a lot of resources online, and exactly because of what you said, that if you're going functional, why not going functional all the way? So, yeah.
I have a question about the performance of such a programming approach, because at least in our use case, you have many dependencies which are probably from one event you need to update many other events or states which have dependencies on their own. So what is the achievable performance with such a system? How do you avoid that you end up with a continuous triggering of updates everywhere for a number of events which may probably need to be processed together in order to achieve a consensus state at the end?
Yeah, it's a good question, because the way reactive programming is usually implemented is by your program will keep track of everything using a graph. And each value, each data stream is a node in your graph. And what you want to do is propagate changes through this graph. So there are many ways to implement this. And there are very simple implementations, but if you use those simple implementations, you will probably run into those performance issues or even design issues where events might not be generated in the order you were expecting. So in this case, it's definitely worth using a better implementation that will use graph theory to tackle those problems in the most efficient way. So, but again, I think those problematics are orthogonal. It really depends on the implementation of the reactive machinery.
Okay, let's thank again the speaker for the good presentation.